Hi, so I'm going to deal with atomic structure and the position of the drawn atoms on the periodic table because there's a link. Um, and what we're about to do here is really important for understanding reactions that will happen in the future. That the reactions happen due to the electronic arrangement, the arrangement of the electrons. And hopefully this lesson will teach you that. So let's make a start. So firstly, let's get to grips with atoms are made of protons, neutrons and electrons. The protons and neutrons are in the center, the nucleus. The electrons are orbiting the nucleus. We've done that before, and we've also said that the electrons are in energy levels. They're in energy levels orbiting the nucleus. I like this kind of diagram, and I don't particularly like you drawing blobs and writing E, etc., where I have to count them. What I like is I like you to write in how many electrons, and that will stop me having to count them. So let's have a look at the proton, neutron, electron. Let's look at their properties. Now, you might see diagrams like this. Now, I was surprised when I went on the internet to try and find a suitable table. I could not find a suitable table that was, in my opinion, of the format that I would like. So I've printed any old table, and I want to tell you that you should change this which we find, you should change it as follows. So the first thing is the charges and masses are not charges and masses, they are relative. That should be relative charge. Relative in chemistry, we do this a lot. We pick something that we compare against. So you pick something, you're going to compare against it, and you're going to call it relative. Like relative atomic mass. We picked a 12th the mass of a carbon-12 atom, and we compare everything to that. Well, relative to something, if a proton is +1 charge, then an electron is -1 charge. That means the charge on an electron is opposite. That's a positive and negative from proton to electrons. The charge on an electron is opposite that of a proton, but it means that the size, 1 plus and 1 minus, means the size of the charge on the proton is exactly the same size as the size of the charge on an electron. So relative. If you do these kind of tables, please label the heading, please label it relative charge. Equally, I want you to label these things relative mass. Relative mass, and then that should be the number 1, and that should be the number 1. Because relatively, the mass of a proton and a neutron are 1 each. And this AMU, which I don't like, is an atomic mass unit. If you take an atomic mass unit and call it like the weight of a proton or the mass of a proton 1, then the mass of a neutron is also 1. And the mass of an electron, I really don't like that. I don't want you to learn that. It might be 0.00054 atomic mass units, but what I want you to learn is the mass of an electron is negligible. So can you learn the mass of an electron is negligible? Can you put relative charge there, relative mass there, and just put +1, 0, -1, and then 1, 1, negligible. Okay, so what should we learn overall from that? Well, what we learn is that the mass of an atom is largely due to the protons and neutrons that make it up. The electrons have such a tiny mass compared to the mass of the protons and neutrons that we can neglect the mass and it will not affect any of our thinking or any of our calculations. Right, let's move on. Right, so how many protons, neutrons, electrons are there in a particular atom? Well, if you're going to do this, you need a periodic table, and I've just drawn what you might see in a periodic table. Lithium, the element lithium, made of atoms, and you got these two numbers. Now the bottom number, the small number, is what we call the atomic number, or in physics they call it the proton number. And the proton number tells you, believe it or not, it tells you the number of protons. Atomic number, proton number tells you the number of protons. Now that number at the top, the 7 in the case of lithium, I want to call that mass number. And mass number means the total number of protons and neutrons all together. So protons and neutrons all together in a bracket, that total number is 7. So if we look at that, I want it to read in your mind's eye 3 protons, 7 protons and neutrons, but 7 protons and neutrons, whether you've got 3 protons, leaves 4 neutrons. And we can start to draw the atom if we know these numbers, how many protons, neutrons, electrons. But we haven't dealt with electrons yet. So let me tell you something about atoms to help you deal with electrons. Every atom is neutral. If you've got neutral atoms, the atoms being neutral, then the positive charges must balance exactly the negative charges that are present. And the positive charges are the protons, they're positively charged. You've got 3 of those. And therefore you must have how many electrons to balance them? 3 of those. The number of neutrons is not going to feature in your logic for working out what is a neutral atom, because neutrons have no charge. So this small number of protons, provided you've got an atom, so long as you've got an atom, then the number of electrons will be that same number. In lithium, 3, and in anything else, the same as the number of protons. So if you look at something generally on a periodic table, the 2 numbers, I want you to know the bottom number is atomic number. Now the top number, this is a bit of a fudge. The top number, I'm calling it the mass number, but on a periodic table, it's not the mass number. It's relative atomic mass, which is slightly different. We'll come back to that. Don't worry about that. At the moment, I'm going to ask you to think of the bigger number as the mass number, and that's the total number of protons and neutrons. So if you have such a thing, if you had mass number and atomic number, then that B would be number of protons, B. That B would be number of electrons, B. Same as the number of protons for atoms. So the smaller number, B, tells you how many protons and electrons there are in that atom. And then the number A. Well, if you use it, the number A is bigger. Subtract B, A take away B, gives you the number of neutrons. So subtracting these 2 numbers will give you the number of neutrons. Let's look at some examples. Now, this is lithium. 3 protons, 3 electrons. Subtract 4 neutrons. Now, I tend to draw nuclei in little boxes to stop me getting confused with the orbits that are circles. Now, you don't have to. If you look at books, they often don't. They normally draw little circles and put whatever's number of protons and neutrons in there. And I quite like that representation because I'm not having to count the number of electrons. I've written in the number of electrons, but again, that's not normal. Normal on the internet and books is to put blobs for electrons. Then you have to go around counting the blobs. Often the electrons in blobs are in pairs, because one of the things in chemistry is that electrons do indeed go around in pairs. They occupy orbitals, and the orbitals, the electron orbitals, are 2 electrons together in one orbital, etc. But we get to talk about orbitals at A level, not at GCSE. So I want you to draw atoms like that, and I want you to be able to use the 2 numbers to get them. And then the final thing is the electrons have to be drawn in orbits, or the proper word is energy levels. You can call them shells, but the proper word is energy levels. So the first energy level holds 2 electrons. The next energy level can hold 8 electrons. And here with lithium, you've only got 3, so you put 2 in the first, and then you have to start a new energy level, the second energy level, and you've only got 1 electron left, so you put that third electron there, and that's your atom of lithium. And drawing atoms is really important. So, arrangement of the electrons. Now, your syllabus at GCSE says you've got to be able to do the diagrams up to 20 electrons. Now, that's because after 20, then we need to teach you a whole different pattern. But up to 20, this simple pattern exists, and the simple pattern works, and I want you to learn it. So, having worked out what's in the nucleus, then the number of electrons up to 20, you put 2 electrons, that's the first energy level, holds 2 electrons maximum. The second energy level holds 8 electrons maximum. The third energy level holds 8 electrons maximum. And if you count those up, 2, 8, 8 makes 18. Therefore, if you're going to draw diagrams of up to 20, you put the remainder in the fourth energy level, and at the most, you should have a remainder of 2 electrons. Practice drawing these, please. You need to be able to draw the first 20 elements, atoms. And what I would like you to do now is to get a blank sheet of paper, hopefully a blank periodic table layout sheet of paper, and on each position, like where lithium is, in the box, I want you to draw an atom of lithium. Where potassium is, draw an atom of potassium. The biggest atom will be calcium. Draw an atom of calcium. You don't have to draw anything bigger. Now, you have to know about bigger atoms, but you won't ever be asked to draw atoms that are bigger. So, let's have a look. Now, this is 19 electrons. Potassium. 2, 8, 8, 1. They're the electrons. 19. In the nucleus, 19 protons, 20 neutrons. And you also need to be able to draw electron arrangements 2, 8, 8, 1. You need to be able to draw them like that to show how many there are in each level. So this goes first level 2, second energy level 8 electrons, third energy level 8 electrons, and the fourth energy level the remainder 1 electron. So 2, 8, 8, 1 separated by commas is a very acceptable, very common way to show electron arrangements if you don't want to draw out the whole atom. But in the early stages, I want you drawing the whole atom. So let's have a look at the other atoms now. You might do the smallest atom, hydrogen. That's just 1 proton in the nucleus with 1 electron. The largest atom, calcium. A metal, aluminium. A non-metal, fluorine. Draw out the first 20 onto a blank periodic table. Now, if I was you, I would pause the video there. Pause it. Because I think my next slide, I've done it. Well, I've not done it. I've grabbed an image from the internet that has it done. All right. So, drawing atoms, practice it. And then, there. I've grabbed an image. See, here they've used dots instead of commas. 2.8.3 means 283. They've drawn it there, 283. In the nucleus, they haven't told me what's in the nucleus in terms of protons and neutrons. What they've done, what they've done there is simply written the symbol. So in the middle of those is a symbol. You can find this on the internet. But what's really important about this is the pattern that I want you to see. Can you look? Group 1. Now that's group 1. That's group 2, group 3, group 4, 5, 6, 7, and group 8 is often called group 0, or it's got like 4 different names. It's annoying. Group 8 is called group 0. They're called the noble gases. They're called the inert gases because they don't react. And any one of those 4 names, you've got to know you're talking about that last column: helium, neon, argon, krypton, xenon, etc. All of those are the noble gases or inert gases or group 8 or group 0. Anyway, if you draw them all out, this is the pattern. Really important pattern. The really important pattern is that the number of electrons in the outermost level, the number of electrons in the outermost level is all of those group 1 atoms of elements all have 1 electron in the outermost energy level. All of those group 2 have 2 electrons in the outermost energy level. All of those in group 3 have 3 electrons. Group 4 have 4, group 5 have 5, group 6 have 6, group 7 have 7. And what you need to know about that last column, group 8 or group noble gases, inert gases, they have full outermost energy levels. Look, that helium, the first level is full, 2 electrons. Neon, 2,8. That second energy level is full. The third one, 288. Argon has the third energy level full, and so on. If we go on to the others that are not there, the bigger ones, you won't ever be asked to draw them, but you do need to know how many electrons they would have in the outermost energy level, and the answer would be they would be full. The first 3 are full. Carry the pattern on. The next 3 that are there on the periodic table, they will be full also. Carry the pattern on with every group though. So group 1, all of those, and carrying on, they all of group 1 elements will have full outermost energy levels. I've messed that up. Let's say that again. All of group 1 will have 1 electron in the outermost energy level. All of group 2 elements will have atoms that have got 2 electrons in the outermost energy level. And group 3 elements atoms will have 3 electrons. Group 4 element atoms will have 4 electrons. Group 5 elements atoms will have 5 electrons. Group 6 element atoms will have 6 electrons in the outermost energy level. And group 7 element atoms will have 7 electrons in the outermost energy level. And finally, group 8 or group noble gases, inert gases, they will have full outermost energy levels. Now that pattern is really important. I want you to learn it because we're going to use it over and over again, and it's fundamental to understanding how these atoms react. In a couple of lessons we're going to be getting onto that, so learn it. So drawing atoms and their position on the periodic table is important. You need to get your mind around that and do that properly, please. Otherwise, you're not going to understand chemistry. So then I'd like to get on to now talking about what a mass number is and what a relative atomic mass is on a periodic table, etc. I said I would get back to this. It is difficult to come back to it. It's one of the more difficult aspects of GCSE. So before I get onto that, I've got this slide. Let me run you through this slide. The reactions of elements depend on and are linked to how many electrons they have in their outermost energy level of electrons. So, learn the pattern on that previous slide. You will never be asked to draw atoms bigger than 20 electrons, that's calcium. But you may be asked how many electrons a big atom has, because you just use the idea of what group it's in. If it's in group 5, it's going to have 5 electrons in the outermost energy level. Even if it's big, you're not drawing it, you just need to know how many electrons in the outermost energy level. So, to summarize, number of protons is the small number, atomic number. The number of electrons is the same as that small number, the atomic number, because atoms are neutral. The mass number is something different. That's the big number, and the big number is the total number of protons and neutrons in the nucleus. To get the number of neutrons, you subtract those two numbers. You take the mass number, subtract the atomic number, that gives you the number of neutrons. The electrons must be arranged 2 electrons in the first level, 8 in the second level, 8 in the third level, and the remainder in the fourth level. And you've got to be able to draw atoms up to 20 electrons. Learn the pattern that the number of electrons any element will have in their outermost energy level, and learn that it's the same as the group number. Even if the atom is very large, you may be asked how many electrons in the outermost level. And finally, group 8, group 0, they have full outermost energy levels. So now I'd like to get on to this rather tricky, difficult discussion about relative atomic masses, and I think that this is the most difficult thing we do at GCSE. I'm going to explain it, but if you don't really understand it, watch my explanations again, read books, talk to your teachers, try and get your mind around it, because it's not that difficult fundamentally. It's just with young minds, it takes a bit of effort to try and understand it. So I'm going to talk about isotopes. To lead me into that discussion, we need to consider isotopes and what they are. And hopefully you've done physics modules where they've taught you what atoms are, and they're made of proton, neutrons, electrons, and they've told you what isotopes are. But if I tell you what isotopes are, you should already know from my lessons that it's the number of protons that identifies for us what element we've got. So something with 3 protons is always lithium. Something with 1 proton is always hydrogen. Something with 20 protons is calcium. So the number of protons identifies what it is that you've got. Atoms with 17 protons are chlorine, 20 are calcium. And let's look at chlorine atoms more closely. Now, there are 2 kinds of chlorine atoms. There's a lighter chlorine called chlorine 35. There's a heavier chlorine called chlorine 37. Now, what makes them both chlorine is that these atoms, both types of atoms, have got 17 protons. Look, 17 protons. 17 protons. That's chlorine, that's chlorine. They're both chlorine as defined by the fact that they've got 17 protons. But the mass numbers are different. The mass numbers on that one is 37. This one is 35. And that's what makes isotopes, where the mass numbers are different. Now let's get to fundamentally why the mass numbers are different. The mass numbers are not different because of the number of protons. The number of protons are 17 in each. So the number of protons has not affected the mass number. It's the number of neutrons. How many neutrons does this chlorine have? 35 take away 17, 18 neutrons. How many neutrons does that have? 20 neutrons. So isotopes, these different atoms of the same element, is what we call isotopes. I'll define it for you in a minute. That's not the definition. That's just me explaining it to you. So when I'm explaining it to you, I'm simply saying that isotopes are atoms of the same element, but with different numbers of protons. The isotopes are atoms of the same element, but with different numbers of neutrons. I should have said neutrons, and I do make these kind of mistakes. You're going to have to get used to that. my mind doesn't think as clearly as perhaps your mind does or your mind should, etc. So sometimes I come out with the wrong word. I apologize, but it will not be the last time that I make such mistakes. I commonly make such mistakes. I hope you find them, and I hope that you don't make them in your old age as I do in my old age. So okay, let's get back to this. Remember me saying that fundamentally the mass of an atom is the number of protons and neutrons. So if the number of neutrons is different, then the masses of these are different. What's fundamental about isotopes is they weigh different amounts. If you've got less neutrons, they are lighter. If you've got more neutrons, they're heavier. You've got heavier and lighter isotopes. But they react. Their reactions are identical. I mean, look, those chlorine atoms are identical to those chlorine atoms. The chlorine atoms will react in exactly the same way. Breathing chlorine gas made of these will kill you in exactly the same way that breathing chlorine made of those atoms will kill you. There won't be any difference. Making sodium chloride salt, if you put it on your fish and chips, the taste will be just the same. What will be different is just the mass of the atoms. Those atoms having 2 more protons are a little heavier than these atoms having 2 neutrons less. I think I said protons there. I should have said neutrons. So 2 extra neutrons make it heavier than this. This one has got 2 fewer neutrons and that makes it lighter. The other thing I want to point out is that when we look in our world and look at all the chlorine that exists in our world, then we find a fixed ratio. We find wherever we look, whether we look in Pakistan, whether we look in the UK, whether we look at some chlorine that's found high up a mountain or some chlorine that's found deep in the sea, we find that there is a ratio of 75% of all chlorine is this lighter type and 25% of all chlorine is the heavier type, the chlorine 37 type. So this ratio, 75 to 25, 3 to 1. The ratio is famous and I'm going to use it in a minute to do a calculation. So look, before I do my calculation, I want you to know what isotopes are. I want you to know that this isotope weighs a bit less than that one, or that one weighs a bit more than that one, because of the difference of 2 more neutrons. So what definition should you learn? Well, clearly, I want you to say that isotopes are atoms. Look, the atoms of the same element. In this case, chlorine. So they're atoms of the same element with the same number of protons, but different numbers of neutrons. There. Learn that. I want you to learn that parrot fashion. The problem I have with tests is when I ask what is an isotope, people write same protons, different neutrons. And they don't really get the appreciation that they are atoms. Atoms of the same element with the same number of protons, different numbers of neutrons. I want you to say all of that. I want you to learn that parrot fashion. And if in an exam they ask you, I want you to regurgitate that into the answer when you give it. So, do all of the elements on the periodic table have isotopes? Well, I don't think they all do, but most of them do. Hydrogen, for example, has got 3 isotopes. Chlorine, as we've just seen there, has got 2 isotopes. You can look up isotopes of any element on the internet. Most of them have isotopes. However, I think there are a few that only have one isotope. And if you've just got one isotope, then you haven't got isotopes, you've just got that one type of atom makes that element up. So what difference does having different numbers of neutrons in these isotopes, what difference does it make? Well, extra neutrons will make atoms heavier, so those atoms will have a bigger mass. I've already said that. I've said to you that the heavier isotopes have a bigger mass. The reactions will be exactly the same. So the reactions don't change. They're exactly the same as the reactions are down to and due to the number of electrons. And the number of electrons is identical. The arrangements are identical. So the reactions will be identical. Electron arrangements for the same atoms of isotopes are the same of the isotopes of an element. That should be of an element. Again, I will make these kind of mistakes. I hope you can correct them. Most elements have isotopes in data books, so you can look up the percentages, like chlorine 75% to 25%, that they're the lighter isotope to heavier isotope. But let's look at hydrogen isotopes. Now, there are three kinds of hydrogen isotopes. There's protium, which is the normal hydrogen. 99.985% is normal, this kind of hydrogen with one proton, one electron. But there is deuterium. Deuterium has an extra neutron, one more neutron, and tritium's got two more neutrons. The number of protons is 1. That makes it hydrogen. This is a heavier kind of hydrogen, and that tritium is heavier still kind of hydrogen. So they are the isotopes of hydrogen. But can you see, this is such a big percentage that most of hydrogen in our world is of this type. Teeny amounts in the world, tiny amounts of the deuterium and tritium exist in our world. So, if the atoms weigh different amounts, what's the average weight of one atom of an element? That's what this relative atomic mass is going to have to take us down that journey. And this is the difficult aspect that boys and pupils find when we're teaching. So let's consider the question, element chlorine, which is made up of two isotopes, 25%, 75%, what's the average mass or weight of one atom? Now, the average weight will not be 36. Now, 36 is a direct average. You would get an answer of 36 if you average 35 and 37, if you had 50% and 50%, and then that 50-50 would give you an average mass of 36. But we haven't. We have to do what's called a weighted average, because we've got a lot more of the lighter atoms, the chlorine 35 atoms. Then our calculation has to be weighted to take that into consideration. And what I urge you to do is to consider percentages, even if you're not, like say you're given the ratio 3:1, 3:1 lighter to heavier, you'd have to convert that to where 3:1 is 4. So let's convert to percentages. Out of 100%, which is 4, 3 is 75%. The lighter one, 25% the heavier one, and then the weighted average calculation is done by writing the mass of 100 atoms across the top and dividing by 100. Look, divide by 100 chlorine atoms to get the weight of one of them. Now, average mass of a chlorine atom here. 37 of them, no, not 30, 25 of them, 25 of these chlorines weigh 37. So that would be the mass of 25 of them. That would be the mass of the other 75 of them. 75 of them are the lighter mass, 25 of them are the heavier mass. Overall, you divide by 100, to get the average mass of one of them. When you do that, you get an answer of 35.5. Now, that I think I reached the maximum recording time on my phone. So I'm just going back. I'm shooting another video just to finish off. I hadn't quite finished my argument, but I was talking about isotopes, and I'd got this far, I think, where I'd explained the calculation. The average mass of one chlorine atom would be the mass of 100 of them divided by 100, which is 35.5. Now, that 35.5 is what we call a relative atomic mass. That's what's on your periodic tables, lads. That 35.5 is on the periodic table. It's not a mass number. Mass numbers are never decimals or fractions. The periodic table that you'll use at GCSE in the exam will be one that will have relative atomic masses. Now, relative atomic masses and mass numbers are similar, but crucially, they're not the same. They're not the same. So what is the definition? And again, I would urge you at the moment just to learn this parrot fashion. You need it for GCSE, and don't try too hard to understand it for now, but the average mass of one atom is relative atomic mass. So relative atomic mass, the average mass of an atom, of an element, and you've got to say relative to, and tell me what is relative to. So relative to a 12th the mass of a carbon-12 atom. Relative to a 12th the mass of a carbon-12 atom is known as the relative atomic mass, and the symbol is capital A subscript R. Now, that is the number that's on the periodic tables. If you read the key, they will tell you that that number is relative atomic mass, and it's usually rounded, but they leave it at 35.5 for chlorine, and they'll leave it at 63.5 for copper. So, with these ideas of isotopes, mass number is the number of protons and neutrons in the nucleus of an atom. Different isotopes have different mass numbers, so they've got different masses because of the different number of neutrons. The weighted average mass of an atom can be calculated if you know the percentages of each isotope that exists relative to each other in our world. You must be able to do weighted average calculations like I did for chlorine. Learn the definitions for isotope, relative atomic mass. I've been through those, so learn those. Relative atomic masses are usually given on school periodic tables. They're rounded to the nearest whole number, except that they don't round the copper and the chlorine. Those are exceptions. Okay, so I think that's the end of that section.